You know, some of the best physics problems aren't just equations on a page, they're really clever riddles. And this one, problem 1.8 from Irodov's classic collection, is a perfect example. Forget the textbook for a second, and think of this as a race between two boats where the winner is definitely not who you'd first expect. So let's dive in and solve this thing together.
Okay, so here's the basic setup. Imagine two identical boats starting at the exact same spot in a river. They're going to race, and they both have to travel the same distance out and back. The first boat, boat A, travels down the river and then comes back up. The second one, boat B, goes straight across to the other side and comes straight back. So who wins? Your first gut reaction might be that the boat getting a boost from the current has a bit of an edge, right? Well, let's see if that's actually true.
All right, let's get into the specifics from the problem. We've got boat A traveling a distance L along the river and back, and boat B travels that same distance L across the river and back. But here's the crucial piece of information. The boat's own speed, what it would do in a calm lake, is 1.2 times faster than the river's current. This little number is going to be the key to unlocking the entire riddle.
So, first up, let's break down the journey for boat A, the one I'm calling the river runner. Its entire trip is happening parallel to the river's current. And that means its journey is really a story of two totally different speeds, one where the river is a huge help and one where it's a huge pain. To figure out boat A's total time, we've got to look at each part of its trip separately. We have the downstream dash and the upstream struggle. The distance is L for both. That's easy. But the speeds, well, they're going to be completely different.
On that first leg, the downstream part, life is good for boat A. Its own speed, which we'll call V prime, and the river's speed, V stream, are working together. They just add up. So it gets a really nice speed boost relative to someone standing on the shore.
But then it has to turn around. And on the way back, it is a completely different story. During this upstream struggle, the boat is fighting against the current the whole way. So the river's speed actually subtracts from the boat's speed, making it go way, way slower relative to the bank.
So how do we find the total time? Easy enough. It's just the time for the trip down plus the time for the trip back. And since we all know that time is just distance divided by speed, we get the total time for boat A by adding L over its fast downstream speed to L over its much, much slower upstream speed.
Now, with a little bit of algebra, finding a common denominator and combining the fractions, we can clean this up into one single, much neater expression for boat A's total time. We're going to hang on to this for a minute. We'll need it for the final showdown. Now, let's see what boat B is up to.
Okay, now for boat B, the river crosser. This boat's journey is way more subtle. It needs to travel straight across the river, at a right angle to the current. But remember, the river is constantly trying to push it downstream. This is where vector physics gets really cool.
I mean, seriously, think about it. If the boat just points its nose directly at the opposite bank and hits the gas, the river's just going to sweep it downstream. It'll end up way off course. So what's the trick? How does it pull this off?
And the answer is just brilliant. It has to aim itself partially upstream. By pointing its nose into the current, it uses some of its power to perfectly cancel out that sideways push from the river. This sets up a really neat relationship between three different speeds: the boat's speed, the river's speed, and the actual speed it achieves going straight across.
And what does that relationship look like? A perfect right-angled triangle, which means we get to use our old friend, the Pythagorean theorem. The boat's own speed is the hypotenuse here. If we rearrange the formula a bit, we can solve for its actual speed across the river. And notice something really important. Its effective speed is always less than its top speed, because it's spending some of its energy just fighting the current.
And right here, this reveals the massive difference between boat A and boat B. For boat B, the trip to the other side and the trip back are perfectly symmetrical. It has to do the exact same maneuver, aiming upstream, on both legs of its journey. And that means its effective speed, its speed relative to the bank, is constant the entire time.
So calculating the total time for boat B is super straightforward now. It's just the total distance, which is 2L, divided by that constant cross-stream speed we just figured out. And there you have it, the final expression for boat B's total time.
All right, the moment of truth has arrived. We've done the physics for both boats. We have the final equations for their travel times. Now it's time to put them head-to-head and finally declare a winner in our river race.
Okay, so here are our two champions, side by side. The expressions for their times, they look kind of similar, don't they? You've got the 2L, the V prime, the V stream, but the details are what matter. Notice boat A's formula has that v prime up in the numerator, while boat B has a square root in its denominator. These little differences are about to decide the whole race.
So, what's the cleanest way to compare them? We just take a ratio. We'll divide boat A's time by boat B's time. If that number is bigger than 1, it means boat A took longer, so B wins. If it's less than 1, A wins. Simple as that. Let's do the math.
And you know what's cool? When we divide the expression for A's time by the one for B's time, the two L terms just cancel out. And after a bit of algebraic magic, the whole thing simplifies down to this beautifully clean expression. To make it even tidier, we can use the variable eta, which is just what the problem calls the ratio of the boat speed to the stream speed, and that gives us our final, powerful formula.
And now, after all that work, we finally get to use that one specific number from the very beginning of the problem. We were told that eta, that ratio of speeds, is 1.2. So let's just plug that value in and see what happens.
The answer is 1.8. What does that mean? It means the ratio of their times is 1.8. Boat A takes 1.8 times longer to finish the race than Boat B. Boat B, the river crosser, is the decisive winner. It doesn't just squeak by, it absolutely crushes it. It's almost twice as fast.
So the math is crystal clear, but I bet for some of you that result still feels kind of weird, right? How on earth did the boat that got a massive speed boost for half its journey lose so badly? The answer is all about the strange physics of averages.
And this is the absolute core lesson of this entire problem. The amount of time that Boat A loses while struggling against the current is so much greater than the time it gained while cruising with the current. Why? Because it spends a lot more time traveling at that painfully slow speed. The penalty of that slow leg completely outweighs the benefit of the fast leg.
So what's the big picture here? What have we really learned? The main takeaway is that in any kind of round trip, the slowest part of your journey has a huge, disproportionate impact on your total time. That agonizingly slow upstream struggle for Boat A just destroyed its average speed. Meanwhile, Boat B, by maintaining a steady, constant pace, even though it was slower than its own top speed, came out way ahead. It's a perfect case of the tortoise and the hare. Consistency can beat raw but uneven speed.
And that really wraps up our deep dive into this classic physics riddle. But this core idea, the penalties on a round trip often hurt you more than bonuses help you, it isn't just about boats. Think about an airplane flying with a tailwind and then flying back into a headwind. Or think about the stock market, where a 50% loss means you need a 100% gain just to break even. The physics of the river race is, surprisingly, all around us. Thanks for joining me on this one.